Hi, in this video we are going to study the properties of the Fourier transforms of even and odd signals. So let us start with the case of an odd or even signal. Let x of t be an even signal with Fourier transform x of omega. Okay, x of t is an even signal, therefore x of t is equal to x of minus t. Now Fourier transform of x of t is x of omega. So what is Fourier transform of x of minus t? In fact, we have the following claim. Fourier transform of x of minus t is x of minus omega. Okay, now we can prove this claim as follows. Fourier transform of x of minus t is from minus infinity to plus infinity the integral of x of minus t e to minus j omega t integrated with respect to t. Okay, so we can here define a new variable, define t prime as minus t. So this means that the differential element dt prime is minus dt. So the integral becomes x of t prime e to j omega t prime minus dt prime. What about the integration limits? As t tends to minus infinity, t prime tends to plus infinity. So this will be, the lower limit will be plus infinity, and similarly for the upper limit, as t tends to plus infinity, t prime tends to minus infinity. So we have this integral. Now we can get rid of this minus sign by interchanging the integration limits. So we have from minus infinity to plus infinity x of t prime e to j omega t prime. We can write it in the following form: minus j minus omega t prime, and then we have dt prime. As you see, this is nothing but the Fourier transform evaluated at Fourier transform of x of t evaluated at minus omega. So if x of t is even, x of omega is equal to x of minus omega. So x of omega is also even. This implies that x of omega is also even. So for an even signal, the Fourier transform of the signal is also even. Now for odd signals, we have a similar result. Let x of t be an odd signal. Now and Fourier transform of x of t is x of omega. Now, x of t is an odd signal, therefore x of t is equal to minus x of minus t. So if you take the Fourier transform of this equality, x of omega is equal to minus x of minus omega. So, this implies that x of omega is also odd. So the Fourier transform of an odd signal is also odd as a function of omega. Now, up to this point, we have assumed that x of t is a general signal, but its Fourier transform exists, but it can be real valued or complex valued. Now let us see the case when x of t is real valued. Okay, so we are going to study this case next. Now let us consider the case of an real valued signal which is even. X of t is real valued and even. Now, since x of t is real valued, x of minus omega is equal to x conjugate of omega. Okay, this is by the symmetry property of the Fourier transform. By the symmetry property of the Fourier transform for real valued signals. Since x of t is real valued, we have this result. X of minus omega is equal to x conjugate of omega. And also, since x of t is even, x of omega is equal to x of minus omega. Okay? Since x of t is even, by the arguments we have just seen, x of omega is equal to x of minus omega. Therefore, x of minus omega is equal to x conjugate of omega, and x of minus omega is equal to x of omega. Therefore, x of omega is equal to x conjugate of omega, which means that x of omega is real valued. So if the signal is real valued and even, the Fourier transform turns out to be real valued and also even, because we already have that property satisfied. Real valued and even. Okay, what about the case x of t is real valued and odd? So again, x of minus omega is equal to x conjugate of omega. This is due to the fact that x of t is real valued. And x of minus omega is equal to minus x of omega. Okay? So this implies that, therefore, x of omega is equal to minus x conjugate of omega, which means that x of omega is pure imaginary and odd. Okay. As you see, since the signal is odd, we have this property satisfied. X of minus omega is equal to x minus x of omega. So a complex quantity which is equal to its complex conjugate multiplied by minus 1, it means that the complex quantity is pure imaginary. Okay. So we have these two cases as well, which are quite important in several applications. For real value signals, if the signal is even, the Fourier transform is real valued and even. And if the signal is odd, the Fourier transform is pure imaginary and odd. Now let us consider an arbitrary signal as our next discussion. X of t is an arbitrary signal, and we assume that it has a Fourier transform, so x of t is Fourier transformable, its Fourier transform exists. Now we know that any signal can be decomposed as the superposition of and it can be expressed as the superposition of its even part and odd part. Now the even part of the signal can be written as x of t plus x of minus t divided by 2. So the Fourier transform of the even part, capital X of x even of omega, is x of omega plus x of minus omega divided by 2. And for the odd part, we can express the odd part as x of t minus x of minus t divided by 2. So the Fourier transform of the odd part is equal to x of omega minus x of minus omega divided by 2. Okay. So this is for an arbitrary signal. It can be real or complex valued. We have these results. Now what happens if x of t is also real valued? In that case, we will be able to express x of minus omega as x conjugate of omega. So let us now look at that case. Okay, so now let us assume that x of t is real valued. So x of t is again decomposed as its even part and odd part. Now the Fourier transform of the even part, we have already calculated that x of the even part of x, the Fourier transform is x of omega plus x of minus omega divided by 2. So it is equal to x of omega plus x conjugate of omega divided by 2, which is equal to real part of x of omega. We know that when you add a complex quantity and its complex conjugate, we get 2 times the real part of that complex quantity. So we have this result, and Fourier transform of the odd part is x of omega minus x of minus omega divided by 2. So this is equal to x of omega minus x conjugate of omega for real value signals. We know that x of minus omega is equal to x conjugate of omega divided by 2. So this is equal to j times the imaginary part of x of omega. Okay, now we can see how we applied these results in a specific example. For instance, we have x of t equal to e to minus alpha t u of t. Alpha is a positive constant, real constant, which is greater than 0. Therefore, we have a decaying exponential, and x of t is absolutely integrable, and its Fourier transform exists. And we have calculated the Fourier transform as 1 over alpha plus j omega. So this can be written as alpha minus j omega divided by alpha square plus omega square by multiplying the denominator and the numerator by the complex conjugate. Now, how do we decompose x of t into its even and odd parts? So let us see this graphically. X of t is the decaying exponential starting from 1 at t equal to 0, and we have an exponential decay as t tends to infinity. X of t decays to 0. So this can be expressed as the superposition of the even part of x of t. So this is the even part of x of t. So we have these decaying exponentials starting from the value 1 over 2, and we have decay in both directions. That means as t tends to infinity or minus infinity, we have exponential decay. Therefore, the even part is also absolutely integrable and its Fourier transform exists. And the odd part of x of t is again can be calculated quite easily. Graphically, okay, let me okay, we have for positive values of t, we have this exponential decay signal starting from 1 over 2. And for negative values, again, we have exponential decay, but now the value at 0 is, or 0 minus, is equal to minus 1/2. So it is clear that the Fourier transform of the even part of the signal by the derivation we have just seen is equal to real part of x of omega, which is equal to alpha over alpha squared plus omega square. Okay. Now, also we see that this function as a function of omega is even. Fourier transform of the odd part is j times the imaginary part of x of omega, which is minus j omega divided by alpha squared plus omega squared. Okay, so by means of this example, we have also obtained the results we have just derived related to the Fourier transforms of the even and odd parts of an arbitrary signal. Thanks for watching.